Okay, so now we are going to move on and talk about, so we have with the eye been talking about a combination of lenses, the corrective lens and the eye lens. But let's do this a little more formally. So suppose I have two lenses and I want to find the final image produced by the two lenses. How do you do this? The same way we did it with the eye, you say the first lens creates an image. The image created by the first lens serves as the object for the second lens. So do lens 1, do lens 2. Okay? Doesn't matter which order you do them in. You use the principle of linear superposition, that is to say the order in which you do the lens does not matter. Okay, but typically we'll do, if I've labeled lens 1 and lens 2, I'm clearly going to do this one first and then this. It doesn't matter though, you could do it in any order. Okay, so if I give you a set of two converging lenses, lens 1 and lens 2 are both converging, I have an object placed here. Why don't we start by figuring out where the image due to the first lens will be formed and what kind of image it will be. So why don't you first answer if you can figure out what kind of image just lens 1 would create. How do we do this? We can draw a little diagram. A parallel ray goes through the focal point, a ray going through the center goes through undisturbed, not perfectly drawn, but where the two meet is where the image is going to form. So it's going to be a real image and it will be inverted. Okay. Now using the thin lens equation, I want you to say something a little more quantitative. Suppose I again take that single object, single lens, the object located at a distance of 2f from the lens to the left of the lens. What can you say about the image? So we already saw that it's a real image and it's inverted, so the inverted part of it is fine. All the options have inverted. But which of the other three is valid? So we know it's a real inverted image. Is it larger than the object or smaller than the object or the same size as the object? So you have to do a little calculation for this. How would you do this? You start with that equation. The object distance over here, I tell you, is 2f. So I can put in 1 over 2f plus 1 over image distance I do not know, but the focal length is 1 over f. So given that object distance is 1 over 2f, what is image distance? I can do 1 over image distance is equal to 1 over f minus 1 over 2f. It doesn't matter that I don't know f, this is simple algebra. I can factor out f, 1 over f, and write this as factor of 1 minus a half. 1 minus a half is a half, so this is 1 over 2f. So what does that tell you the image distance is? The object distance is twice the focal length, the image distance is, where is the image located? Same distance, but on the other side of the lens. So the image distance is also, it just so happens because of this algebra, that if the object distance is 2f, then the image distance is also 2f. So remember the magnification? Magnification is negative image distance over object distance. Object distance and image distance are equal, so this is negative 1. So it tells you the image is inverted, it's negative. The magnification is 1, meaning it's the same size as the object. It doesn't matter that you don't have numbers, you can always do this algebraically. Okay, so now that we know how to do one lens, we've reminded ourselves how to do one lens, let's do the second lens. So this is the first lens, it forms a real inverted image at that point. Given the object distance, we can find the image distance. Now this is step 2. Ignore lens 1. Ignore the original object. Just focus on this. This is now my object. Okay? And I'm only looking at lens 2. Okay, I can forget about everything else. So now I use this as my object and put it in front of lens 2. What kind of image am I going to get? If this were the only object for a converging lens, once again, the object distance is greater than the focal length. So if I have an object that's in front of a converging lens, I'm going to get a real inverted image. Inverted relative to this. But the final image is inverted relative to this. So the final image is the same orientation as the original object. So inversion, inversion come back to the same orientation, and of course the size has changed depending on the placement of the lenses and the object. Okay, so you get finally with lens combinations you can get, so usually you think with a single lens it's either real inverted, virtual upright, but with lens combinations you can get any of these things. Okay? So you have to do it step by step to see what it is, whether it's an inverted image or upright image, and whether it's reduced or magnified. But once again, it's really a single lens problem where I'm doing one problem then a second problem. Okay? So if you think of it that way, it's not terrible. Okay. What happens if the second lens is placed? So remember here, the second lens was to the right of this image. But now, what if I took this second lens and I moved it here, to the left of the object? So here's my first lens, I have my image, here's my second lens. So which of these statements is true? How do I think about, remember I said that the first image serves as the object for the second lens. And what kind of object is there? Is there an object? Is it a real object? Is it a virtual object? What do I even mean by a real and a virtual object? Okay. So what you say now is, if the object is behind the lens, the object distance is negative. And a negative object distance is called a virtual object. Why would you think it's a virtual object? I mean, it's only an object. What is really happening is that the light rays are coming through this makes them converge, this makes them converge differently. So I have a superposition of these. The light rays aren't actually forming an object and then forming a second object. The light rays are only forming one image. I mean, the light rays aren't forming a first object and then a second image. They only form one image. But for us to process this mathematically, it makes sense for us to create this two-step process. So we do one lens and then the other. It's for mathematical ease and not because it's actually physical. So for mathematical ease, we say that the second object, if it's behind the lens, the first image, which is the object for the second lens, if it's behind the lens, it's a virtual object. It has a negative object distance. So the image will form by using, again, ray diagrams where this is the object for that lens. Okay? So you call that a virtual object. So you remember I had shown you this slide earlier. That is what this statement means, that the object distance is negative if the object is behind the lens. You'll never have an object behind the lens for a single lens. You only have an object behind the lens for a lens combination. And this can be for any number of lenses. You go into any physics lab which does optics, you'll see a series of lenses that are in some pathway of, say, your laser beam. Focal microscopy, when you do it, you're basically taking a laser sheet and you're illuminating different slices of your sample. So you create a 3D image by moving the focal plane of your microscope. So, you need complicated optics for this, which means you need many lens combinations and you need to set up these rules so you can do the calculations and figure out what's supposed to be happening. So then, the image formed from lens 2 is that you just do the math and you figure out if the second object distance is negative, remember? So the second image distance will be positive. It will be to the right of this lens. So though it's a virtual object, I'm going to get a real image out of this in this particular circumstance. So when I do the ray diagrams for this, I finally get that my final image is somewhere there. Okay, so let's do a quick calculation, do a problem of this. Suppose I gave you the following combination, and for ease, each square over here is 3 centimeters on the side. So if you read off this diagram, what is the object distance for the first image, first lens? 15 centimeters. Okay, what is the focal length of the first lens? 6 centimeters. Okay, so you do a calculation. The first image is going to be formed where I take the focal length to be 6 centimeters, the object distance to be 15 centimeters. 15 minus 6 over 15 times 6, you're going to get 1/10. So your image distance is at 10 centimeters, which is to say I draw it 1/3 of the way between this and this. That's your first image. If that is at 10 centimeters, what is the object distance for the second lens? Because it's 3, 6, and then 2 out of 3 of that. So 3 plus 6 plus 8. So the object distance for the second lens is now 8 centimeters. What is the focal length of the second lens? 3 centimeters. You know the focal length is 3 centimeters. You know the object distance is 8 centimeters. And you say, okay, the final image distance is going to be 4.8 centimeters from lens 2. So you take 4.8 centimeters from lens 2, and that's your final image. How do I find the magnification of the final image? Once again, to do magnification, it's a 2-step process. You first do this magnification, then you do this magnification. For this magnification, I should be taking negative of di1 over do1, correct? For the second magnification, I should be taking negative of di2 over do2. Those are related. do2 you get from this. So final magnification is the product of the two magnifications, which is the height of the final image over the height of the initial image. And you just get that by using those numbers that we had on the previous slide. So we had first image distance was 10, first object distance was 15, second image distance was 4.8, second object distance was 8. There's a negative and the negative, so they cancel, and you get finally that you have a final image that is the same orientation as your original object. Okay, so it's upright and it's reduced. Okay, so the way you do a microscope is exactly this. Okay, so for a microscope, this is also what happens. For a microscope, you have two lenses. You have an objective and an eyepiece. The objective lens is this thing that you move around over here, which is near the sample. The eyepiece is nearer where you're looking. So I have two converging lenses, and very often this distance between them is also something you can change. Okay? So you have some variability. So depending on the placement of the lenses and the power of the lenses, you can get different magnifications. So if all of you have used this simple kind of microscope, you know that on the lens is written 10x, 20x. 10x, 20x and all refers to the magnification. So how many times magnified it is for that particular lens. Okay, so what you get is finally a real image of your object.